Hi, today we are looking at something called connected rates of change, and in this video we're going to be introducing what that is, how to approach it, but there will be a second video where we specifically look at more hard questions within this topic area. So the first thing you're wondering is, what is connected rates of change? Well, ultimately, if you understand how the chain rule works, you kind of already basically have an understanding of how connected rates of change works. It's the idea of starting off with a derivative of some sort. Let's say we had a dA over dx, and realizing that we may want a different derivative. Let's say, for instance, we want dy over dx. And realizing that all we've got to do to the derivative we have is multiply it by another derivative that will conveniently cancel out the things we want to cancel out and leave us with the derivative we want. So for instance, in this particular case, we don't want the dA, so therefore we're going to multiply by a second derivative with a dA on the bottom, because that will cancel out the dA on the top. And then we want a dy on the top that we don't currently have, so we're going to need to introduce that as part of our multiplying by that second derivative, because then if we multiply these two derivatives, we do end up with dy over dx. So it's that same idea we had been using with chain rule, multiplying two derivatives together. Certain parts of the derivative notation cancel out, if you will, to leave you with the derivative you want. So a very quick example would be something as simple as this. We'd be given that dh over dt is 5, and we want dA over dt. Specifically when h is equal to 3, worth pointing out though, as soon as you're given in these sort of questions a particular value of a particular variable, kind of plugging that in is the very last thing you'll do in the question. So most of the question you're dealing with things in terms of algebra when you can. So therefore we want dA over dt, but we've got dH over dt. So it's going to involve something to do with dH over dt, but that's not going to be the final answer. We realize that we are going to multiply by a derivative with a dA on the top, because we currently don't have a dA at all, so we're going to need to multiply with a derivative with the dA on the top to introduce the dA. And then on the bottom, well, we currently have a dH on the top that we don't want, so we're going to need to multiply by a derivative with a dH on the bottom to then effectively cancel out that dH. Cool. Good news is, out of these two things, as we already said, we've already got the dH over dt part, that's 5, but then we don't have the dA over dH part, so that's something we're going to need to separately find. Good news is, dA over dH will be found by simply differentiating the equation linking a to h. So therefore, if we differentiate the h's, we will end up with dA over dH being 18h squared minus 7. So then therefore we now got that, we can now plug that in as part of our wider expression. So therefore it will be 5 lots of our dA over dH. And then that is dA over dt, but we want to find dA over dt when specifically h is equal to 3. So therefore dA over dt at h equals 3 is going to equal 5 lots of 18 times by 3 squared minus 7, and we've just got to type that all into the calculator. So that will be 9 times by 18, which is 162, take away 7 is 155, which would be 775, I believe. There you go. So that's the answer to that example. So at its base level, certainly in terms of the algebra, this is not really any more difficult than what you do with chain rule. The thing that makes this topic sometimes a bit more tricky, though, is that it involves words. So that's kind of what differentiates this from just a generic chain rule question, is instead of being given an example like the one we've been given for this first example, which is, you know, fairly algebraic, instead you're given a lot more words to deal with. So there's certain things you have to be on the lookout for when you're given a paragraph of words to know that it's going to be one of these questions to start with. The first thing to be aware of is you're looking for words to do with the word rate, because ultimately as soon as you see the word rate, instantly know there's a derivative involved. There's going to be d something over d something else, and we'll fill those in a bit. The crucial thing is then you're deciding what those letters are, and the first thing you're trying to look for is what is the rate that you are looking at. What is it the rate of? So in this case, it's the rate of change of y. Now, whatever you're looking at the rate of is the letter that's going to be going on the top. So it's the rate of change of y, so therefore dy on the top. And then they'll sometimes have this extra little sentence after that's talking about with respect to x. That's basically saying what's causing the change to happen. And therefore, that is telling you the letter that goes on the bottom of the derivative. So the rate of change of y gives the fact that it's the y on the top, and then the with respect to x part gives the fact that it's the x on the bottom. However, that's with that very specific wording. Sometimes they'll be a bit more vague than that, and sometimes they'll just say the rate of something. What are you going to do again there? Also, the other thing is sometimes, as I've kind of already implied here, they won't bother always to write the word change. They'll just say the rate of something rather than the rate of change of something. That doesn't make a difference. It's more that just they're saying just the rate of Q, and then they're not mentioning a second letter. Well, the thing to be aware of straight away is, of course, because they're mentioning the rate of Q, just like before, that's corresponding to the letter that appears on the top. So therefore it's dq over d something, but then what decides the something on the bottom? Well, in general, the thing to be aware of is we naturally generally assume that if things are changing, things are just changing over a time period, or we sometimes say in English language that things are changing over time, if you will. And that is a phrase that actually has a double meaning when it comes to the maths. When we're saying it's changing over time, it also secretly means that literally when you're looking at the fraction for the derivative, it's changing over time. In other words, time is the thing that's on the bottom of the derivative fraction. So basically, if they just say the rate of something without mentioning the with respect to part, assume basically time is on the bottom, dt is on the bottom. Other things to be aware of when it comes to the words, just a throwback to something we dealt with in the AS content. You're expected to know that increasing means we've got a positive derivative, decreasing means you've got a negative derivative. So it just tells you whether you're dealing with a positive or negative number when it comes to that sort of stuff. And then also a little side note, it's also worth reminding you that you can flip a derivative upside down by doing 1 over it. So 1 over dx over dy is something we looked at before as being the same as dy over dx in another part of maths. So putting all those things together in a second example. So we've got this scenario, and as always, it's important that you look at any letters they have given to you. In this case, they've given us the A is area, and then we've got this other letter R in this case. And basically, we've got to deal with the fact there's all these extra words as well. So the first thing to point out is the fact that they're mentioning the area, and then there's the rate of the area. So that's telling us we're talking about dA. It then doesn't mention with respect to, so therefore we make the assumption it's dA over dt. There is admittedly another hint at that being the fact, because the units for the rate is 3 centimeters squared. That centimeter squared is referring to the area part, but then the per week is a measurement of time, and therefore that's the per bit is telling you is on the bottom. So that's another way of viewing it. The fact it's 3 centimeters, therefore means dA over dt equals 3. The other important point is that it's increasing at a rate of 3, so that means that's why it's dA over dt equals positive 3. Okay, we want to find the rate at which R is increasing. So that means, and again, doesn't say with respect to, so that means we want dr over dt. So we then just got to think, what have we got to do to the derivative we know, which is dA over dt, to get the dr over dt that we want. So therefore, you're going to want to multiply by dr on the top, because that will introduce the dr that we don't currently have. And then we're going to have the dA on the bottom to cancel out the dA that we already currently have but don't want. Cool. So we've just got to find dA over dr, except we might be realizing that we're not going to find that in one step, because instead it's going to be easier to find dA over dr by, of course, differentiating the equation A equals in terms of r. Now we've got a pi r squared there, and if we're differentiating r's, just be aware pi is just a number, so that's no more scary than differentiating 5r squared. Just treat the pi like you would treat the 5 normally. So therefore, still the usual trick of timesing by the power, taking 1 off the power. So pi gets multiplied by 2 to get 2 pi, because of the 2 in the power. And then taking 1 off the power means we're going to have power of 1, so it's just 2 pi r. And then adding on 10r differentiated, which differentiates to just 10. Cool. But of course, realizing that that's dA over dr, we want dr over dA upside down basically from what we have. So that's going to be 1 over dA over dr. So that'll be 1 over 2 pi r plus 10, like that. Cool, we now have all the bits we need. We can now plug it all in together. So our dA over dt times by our dr over dA will end up with 3 over 2 pi r plus 10. However, we want dr over dt at r equals 2. So now we've got to plug in r equals 2 into that expression or equation that we had before. And that's when you're going to want to use your calculator. So plugging that into the calculator, you will get an answer of, to 3 significant figures, 0.133 to 3 significant figures. The question didn't say what accuracy it wanted it to be, so therefore the default in Maths A-level is 3 significant figures. Also worth pointing out that the fact that this is a wordy question means it's a good idea to put your answer back in context at the end. And therefore, I mean, okay, the question didn't say that it's radius, but it is radius basically. So therefore it's a length, and therefore we're ultimately going to realize that we want this to be in the units of centimeters per week instead. So always good to use units and things like that to put your answer back in context at the end. Cool. There you go. That's how we do connected rates of change. It's all just about doing the same sort of maths we're doing with chain rule already earlier in the course, but now with this added layer of having to deal with words as well. Lovely stuff. See you in the next video where we're going to be looking at some harder connected rates of change questions.